chosen that first. So, because we have already explored all the cost nodes till G, G must be the least cost solution. So both BFS, DFS didn't give us optimal solutions. Uniform cost does, after expanding so many nodes, right? So we can also keep track of how many nodes we expanded in each algorithm. Just so happens that DFS expands least number of nodes for this case, but this can also potentially expand a lot more nodes for other problems. BFS we have expanded a lot. Uniform cost we have expanded a lot. So basically, from what you learned from lecture, you are expected to expand less number of nodes if you use A star. We'll get to that. Before that, we'll see what greedy search does. So this is interesting. Here, okay, you guys note it down, and if you stop, I'll start. Hello. So, should we move on to the next problem, or do we need some time? Okay. So we are not discussing greed.
Solutions for this term, right? SACD is also the solution.
Yeah, if you continue, you'll get more solutions. We are interested in the first solution.
So is it required that I need to expand both the nodes with the same weightage?
You choose in any order.
So like what if if I choose gets the higher weight later on, how it
Yeah, that you have no clue of knowing at this point.
So
From whatever you know, both are equal to you.
So like if I'm having a 6 weight on a C node right now,
Yeah.
I expanded one, and before going to 7 I should also expand the other C as well, is it?
Yeah, before going to 7, you will expand all 6 or less first. So you won't go to 7 until you expanded all the items which are less than that.
So I need to expand both C before going to 7?
Yes, both C's. We did that. Yeah. We go purely on the cost basis. Whichever is the least cost, we'll expand. So we can't go to 7 before 6. Where?
At the end of the line.
Here?
After A.
Yeah, that was causing actually a loop. We missed it. So it should have been never have been there in the first place. So when you write programs, so the program will take care of it here. We need to be more careful. Okay, so we'll move on to greedy search. Maybe that's the last one which we can cover in this section. So what greedy search does is, here we know information, the heuristics basically. These are additional information on top of this graph saying that from this node, estimated cost to goal node is 2. It may be true, false, it can be less, more, and all sorts of things. So ideally we would like the estimated cost to match the exact cost or the least cost, right? But it can be less than that, in which case we call it admissible heuristics. And all that you might have seen in the lectures, what are the properties of admissible heuristics, how it helps in A star and so on. We'll get there in the next section. It can also be more than 2. It may, here somebody may say that the heuristic estimate is 3. So even though we know that there is a path to 2, any questions? Basically the way it works is that whenever we are expanding a node, we don't have the knowledge of the full graph. Even though here we can see the entire graph, typically in the beginning we only know about start state. We know that this is the start state and this is the estimate. And we won't know anything else. And somebody will give us a successor function which if we apply, we will know that these are the successors. Okay, sorry, this is the start. Then we will know that if we expand, we will know these 3 are the successors. Only then we will know. Until we expand, we don't know anything about the graph. That's all. So that's why this heuristic estimate helps. So whether that is more or less or exactly equal to the best cost, we don't know at the beginning, because we don't have the knowledge of the entire graph. When we get here, we'll know that the children of this is this and this. We won't know what is the exact cost to goal. For example, here it is said that the estimated cost to goal is 2. Here we can see the entire graph, so we can make out that no way, right? But when we are actually doing the search, we won't know what is the remaining of the graph. So only upon expanding, we'll know that the children are this, and then we go here, then extra, right? So the way greedy search works is that you always take the least estimate valued node first. So you go based on the heuristic. If somebody is telling you that estimated cost from this node to goal is 0, you will expand that node first. I am very greedy, right? The algorithm works like that basically. So you take start state, you expand that, you put all these 3, and this one is telling that from here estimated cost is 1. So we'll greedily choose this one instead of the other ones. We won't care about how much cost already we spent in reaching the node. We'll only see from here now how quickly, how greedily we can reach the goal state. So we'll choose the one with least h value. Okay. So once again, we'll do something like this with all the states, and now the priority is decided based on the h values. So you don't have to calculate the cost values upfront.
So when we are considering further nodes, do the h values add up? As in like how the
No,
cost
h value is fixed. For this
No,
node,
as in like, so A, C, after start A, C. So when I'm considering that part, do the overall h values like the paths with
no. The h value doesn't work like
H value
that.
decision is a new.
Yeah, for that state, that is the h value. So for this state, the estimated cost to goal is this, that is fixed. So estimation shouldn't add up, right? What should add up is the cost till reaching this node and this to goal state. That makes sense. That's what happens in A star. We'll see next. Somebody is giving us for now. So there are.
Not this, I'm not talking about this. Suppose in real life, you take a.
In real life, you can design your own heuristics, saying that, for example, let us take an example. Let us say I am in this corner of the room, and let's say it's a grid-like structure, and I want to reach that corner. So one heuristic could be, if I am at 0, 0, that is 3, 4, mod 3 plus mod 4, right? Something like that. That serves as an estimate. How accurate it is, all that properties can be proved, etc., etc. That's how generally estimates are designed. A quick way of telling how many steps will it take there. But actual number of steps may depend on what are the obstacles in between and so on. So, but instead of accounting for all that, which would mean we are actually conducting the full exhaustive search, we'll just take a quick estimate, which is the Manhattan distance, something like that.
So for estimating the cost, do we even include estimating the heuristics, the cost of estimating heuristics?
No. So now you are talking about performance. How much time will it take in coming up with that edge, right? So all those things we'll discuss later. For now, let us assume that somebody has given us these estimates. In performance, it matters, but what is the actual solution value? It doesn't matter, right? Now for all these cases, let us assume that we have infinite time. So we'll get to the performance metrics afterwards. So let us do it. Anybody who wants to do? Okay. again start, H value is not given, not needed, let's say. So we'll expand start. What are the things? A, B and D. Now what is the one which matters? The H values. 2, 5 and 1. Now which one will we choose? D. D. Right? What are the children? B, C and goal, ignoring start. Okay? B, C and goal. Now what is 5?
No, that goes to D. That goes to D.
Oh, sorry. Somebody's paying attention. Okay. So, what are the costs? B is 5, 2, C is 2, G is typically 0. Okay. So, this is not given, but you can assume. G's heuristic estimate will typically be 0, right? Because you are the goal state. Any function which we use for calculating, it should be very good. So, now which one will we choose? G. Yeah. So, what is the path? G to D to start. Same as this. Okay. So greedy can be extremely fast, although its solution won't be same as optimal and most likely will actually be very bad, may actually be bad in practice. But it can be very fast. Any questions so far? So A star, maybe you guys can do yourself at home. We'll take a break, or do you want to do it here? You want to do it here? Oh, okay. Okay. Just note it down. So you guys can start on A star. The way A star works is the combination of uniform cost and greedy. So for uniform cost, we took what is the cost from start node up till here, and here we are only using estimates. Here we'll combine both. So for each node, we have to keep track of the cost up till here and the heuristic estimate. And we keep track of that sum, whichever is the least, we will expand that. So less f value. So we call this the g values, the cost from start node to the current node, and the estimates we call h values, as we saw, right? Now for A star, what we do is f values, which is g plus h, and we always choose whatever is the minimum value node. This one sort of tells you the promise of the node, right? I have spent so much effort coming here, and I am estimated to spend so much more. So overall promise of this node is so much. Now, whichever promises me the least amount of cost, we'll take that and see whether it's goal.
So when expending a
Node.
child and then expending again for the child, so do I add the path cost plus
Yeah.
h values?
So G is obtained this way,
Okay.
H is fixed. So you add the cumulative G and the constant H. So okay, so let us see how A star looks. Anybody wants to do? Okay. A star should be fairly simple because it tells us that it will minimize the number of nodes expanded, guaranteeing optimal path. Initially we have start node. What is the F value? Let us assume H is 0. Doesn't matter whatever H is, right? Some K. Who cares? So G value is 0 for, so 0 plus K. And we have to expand it, right? Now, what are the children? A, B and D. What are the G values? 2, 3, 5 plus H values 1 plus 5 plus is, okay. So this is 4, 8, 6. So we'll expand A. So C. What is the
10.
2 plus 4, 6 plus 2, 8, right? Okay.
Can you just explain?
So the G value of A is 2. So the G value of this will be 2 plus AC, which is 6, and its H is 2.
but you don't consider the cost to reach from start to A?
That is what we consider for G values. H is fixed for a node. From here to goal, this is the estimate, that is fixed. Doesn't matter from where you come up till here, from here to goal estimate is fixed.
So like we consider from going from S to A, we consider heuristic value of A.
No, for S to A there is no consideration of heuristic value. We'll go to A and we spent this much of effort, 2, that is the G value.
Yeah.
So heuristic has nothing to do here. From A to goal, the estimate is 2. The estimate is
by
this.
heuristic I mean H value. Sorry.
Yeah, H value is for this particular state, not for this transition.
Okay.
So you can get here something like this, but the H value is same, 2. It is its estimate to reach goal, reach the goal.
Okay.
Nothing to do with how you reach there.
So when we are on C, we don't consider the H value of C.
H we do. So we'll consider the cost from reaching to start to here, which is G, what we did in uniform cost. H is given. We add both. Start node to current node cost, whatever we traversed actually, and the estimate, which is fixed. Okay. So we'll expand D, right? Because that is the least cost. D has B, C, and G, ignoring start state, all of which are possible. So what are the G values? 5 plus 4, 9. C is 5 plus
1.
1, which is 6. G is 5 plus 5, 10. H value for B is 5. C is 2. G is 0. This is 10. Now which one will we take?
We take C.
One of the C's. Let us take any one of them. Let's take this one. What are the children? A, D, and B. Can A happen? No, because it's here on the path to start. Can D happen? Yes. G happen? Yes. So what is the G value here? 6 plus CD. What is the G value? 6 plus CG. 8. This is 0. This is
1.
1. Okay. So now which one? Any one of these 3, D, G, or C. This is tough. So you can expand C or D or G, any tie breaking. You can do other tie breakings at home. I'll choose this. Okay. So what is the path? G to C to
C to A and A to start.
C to A and to start. And the cost is 8. This will be the cost because H is 0 and okay. So now this turned out to be the optimal solution because we know that this is optimal. Okay. This could have been optimal or not optimal. In which case it could have been optimal?
Admissible.
When this heuristic underestimates the actual cost. Basically, if this heuristic is less than or equal to the actual cost to the goal node, then this guarantees providing us the optimal solution. If that is not, if it is random heuristic, which could have been inadmissible, it could give us something other than 8, maybe 9, 10, any other of those things. Okay. And the proof is kind of intuitive, right? If this was admissible, then you have actually traversed all paths of f value less than or equal to the g of the current node you are expanding before expanding that node. So there exists no path which has lesser g, which could have been goal, which is less than the current f value we are expanding. Yeah, that probably you'll get more details in the textbook and the lecture. So is the heuristic admissible here?
No.
No? This one underestimates clearly because the best is 3 to the goal. This one, okay. This one underestimates, yes.
Yeah,
Best
all
is 2
understood.
and fine. This one, does it underestimate? Yeah, any path will be greater than 2, right? This one doesn't matter. This one, even the best path looks to be 3, 7 I think.
Yeah.
So basically the heuristic given is an underestimating heuristic. So we'll be guaranteed to know that 8 is the optimal, even if we didn't do uniform cost search or any other things. Okay. Any questions?
So you would use priority queues for greedy and daystar as well?
Yes. Even for uniform cost search.
Yeah.
Yeah, all 3 are priority queues, except. Wherever we wrote numbers basically means priority queue, right? Okay, so that's it then for this section. Hope you learned something. I don't know. So next is in the other building, which is on the website. The BOAC 190, I think.